All right, in this section, we're going to talk about inverse functions and the properties of inverse functions and what it means to be invertible. We talked about inverse functions a little bit in chapter 1. But before we get started, I want to revisit what it means to be a function. So let's take a look at these two cases. We got basically two examples in one here. The first part of this example, we're looking at a ball that's tossed up into the air with an initial velocity of 20 meters per second. And we're given a formula for the height above the ground after t seconds after it was thrown. Okay, so we have a function. And the first question is just asking, what is the height of the ball after 3.5 seconds? So since we have the function, we can just plug in, we can evaluate h of 3.5 just by replacing t with 3.5, right? Plug in t equals 3.5. I can tell already I'm running out of room here. 3.5, right? And then plus 1. All right, you can put that in your calculator. I got 9.75 meters. Okay, and I can do that for any value of t I want, really. Now, there's probably some restrictions on the domain of this function, right? Because this function doesn't hold before the, for negative values of t, before the ball was tossed. It also doesn't hold once it, comes back to Earth and you either catch it or it hits the ground. So there's probably some restrictions on the domain that aren't shown. But we could take any value of t in the domain and we could find exactly one height, right? So the ball is only at one height for every value of t. All right. Now, the second question is asking how many seconds after being tossed was the ball's height 16 meters above the ground? All right. Now, I could just set up an equation. I could say, okay, like the height is 16 meters, and I want to find the t values. 20t plus 1. I want to find the t values of that satisfy this equation. I want to find the t values in this case when t is equal, or when h is equal to 16. So this is a pretty simple quadratic equation to solve. I can just move everything to one side. I can write 5t squared minus 20t, and then if I subtract the 1 from that, I get plus 15 equals 0. And that's a quadratic we can solve. I would factor out the 5 and then factor that quadratic. That's not the point of this question though. So we're going to refer to the graph here. So I have actually a graph of the function. And you can see that if I'm looking for the height when it's equal, I'm looking for the times when the height is equal to 16, you can see I get a couple of different values. If I got a value here at 1 second and I got a value here at 3 seconds. So it passes that height once on the way up and once on the way down. And so from the graph, I'm just going to say from the graph, rather than actually do the math and evaluate or find what the t values are using algebra, I'm going to look at the graph and I can see that this happens when t is equal to 1 or 3 seconds. Okay? And the point of this is that I can't express time as a function of height, right? Because for certain heights, those occur at more than one time. So my point is that we can't express time as a function of height. GHD. All right, so that's the point. So we have a function that doesn't go both ways. We have a function for height in terms of time, but we could not express time as a function of height. unless we restrict the domain. Now we could restrict the domain. We're going to get into that as well in this chapter or in this section. But if I just wanted to know, what, I was just interested, it's like on the way up, right, where t is less than 2, I could restrict the domain to t between 0 and 2, and then I would get 1 time for every height. Okay, we'll get into that. Let's look at this other function, though. This other function, let me scroll back up here to the beginning so we can see what we're talking about. We have a depreciation problem. A car was purchased for $20,000 and it depreciates at 20% per year. And we're given this exponential formula for the value of the car over time. Okay, so we can put in, the first part of this question is just asking us to evaluate v of 2. That's the value of the car after 2 years. All right, so we're just going to take the 20,000 and take it times 0.8 squared. So let's see, I didn't calculate that. 20,000 times 0.8 squared. It looks like it gives me, after 2 years, the value of the car is $12,800. Okay. So, and I could do that for any value of t. If I put in a value of t, I'm just going to get one value for the value of the car. Okay. So each time corresponds to one value. And so we can express value as a function of time, as it's shown here. So now we're going to go the other way. So now if we're given a value, we want to know here in this case how long does it take for the value of the car to reach $8,000. Okay, so now to solve this analytically using algebra, we need logarithms, and we haven't studied logarithms yet. So I'm not going to solve this with algebra. I'm just going to use the graph, which I have below. So let's look at the graph here. And you can see that, okay, here's $8,000. And if I go across to the graph, you can see there's just one time. And it looks like it's a little bit more than 4. So let's say 4.1. All right. So just using the graph, let's see, I'll just say from the graph. It looks like v of t equals 8,000 when t is equal to approximately 4.1, and our t is in years. So I'll say 4.1 years. That's my best estimation. So in this case, we get one value of time for every value for every value of the vehicle, right? So if I give you a value of the vehicle, you could tell me the time that it reaches that value. So in this case, we could express. So we could, if we had the right tools, the right algebraic tools like logarithms, we could express the we could express the time as a function of value. We could express the time as a function of the value of the car, right? Because every value occurs at exactly one time, right? So so we can express the time as a function of value if we wanted to. All right. I mean, there's never a case where one value would occur at 2 different times. So that's the big difference between these two functions. One of them we can reverse this depreciation problem where we're looking at the value of the car. We could reverse it, right? We could reverse it and theoretically express time as a function of value, whereas we cannot do that for the other function, the function where we toss the ball up into the air. And that's just because if we tried to do that, we would not get a function. Okay, we would not get a function. And so the first function where we toss the ball, that one is not invertible. The second function is invertible, all right, because we could switch the input and output and write a function for time. Time is a function of value. We were given a function for value as a function of time, and we could reverse that. All right, so it would be considered invertible. All right, so I think I've talked enough in this video, and I'll meet you in the next video to talk a little bit more about inverses and invertibility.